Control charts for continuous data. Keeping processes stable. Don't just look at the result. Watch the story unfold. Why use control charts? Imagine driving a car without a dashboard. No speedometer, no fuel gauge. How would you know if you're running safely? A control chart is your process's dashboard. It shows, are we stable? Are we staying within limits? Are there warning signs before things go wrong? Key message: control charts let you monitor your process over time, not just see a snapshot. Why continuous data needs control charts? Continuous data, priced measured on a scale, time, length, weight, temperature, etc. Examples: diameter of a pipe, patient's blood pressure, call handling time. Continuous data needs special control charts like X bar R, X bar S, individuals charts, because they track measurements, not just counts. Facilitator tip: ask audience, who here has used a thermometer, stopwatch, or scale? You've worked with continuous data. Example: manufacturing. A factory tracks the diameter of metal rods. Target equals 10.00 millimeters. Tolerance equals plus or minus 0.10 millimeters. Use an X bar R chart to monitor. Is the average diameter shifting? Is variability increasing? Instead of waiting for customer complaints, we catch the drift before defects happen. Example: service. A hospital measures average patient wait time every hour. Goal equals patients seen within 20 minutes. Use an individual's chart to monitor: is wait time stable? Are we trending toward unacceptable delays? Message: whether it's a machine or a patient queue, control charts watch patterns, not just averages. Why control charts matter? Detect problems before they create defects. Avoid overreacting to normal fluctuation. Distinguish common cause, normal variation, versus special cause, unexpected issue. Build confidence in process stability. Facilitator. Analogy: control charts are like an early warning radar. You see the storm before it hits. Fun fact to engage audience: the first control chart was created in 1924 by Walter Shewhart at Bell Labs to monitor telephone manufacturing. Facilitator tip: almost 100 years later, we're still using control charts because they work. Continuous control charts. IMR, X bar R, X bar S. 1. Why continuous control charts? Continuous data equals measured on a scale. For example, weight, temperature, time length. We use continuous control charts to monitor process stability over time, detect shifts or unusual variation, keep processes in control, prevent defects. Main continuous control charts. IMR chart, individuals and moving range. X bar R chart, mean and range. X bar S chart, mean and standard deviation. Key components. Individuals chart. I, plots. Each individual data point. Moving range chart, MR. Plots range between consecutive points. Example: manufacturing. A machine fills bottles with 500 milliliters of liquid. We measure every 10th bottle. IMR chart shows. I chart. Each bottle's fill volume. MR chart. Variation between each consecutive bottle. Detects small drifts in fill volume, even with single data points. Example: service. Tracking loan approval time for each application. I chart. Approval time for each application. MR chart. How approval times vary from one app to the next. Quick detection if an unusually long short processing happens. Interpretation. Are points inside control limits? Any trends, patterns? Any sudden spikes, drops in MR? XR chart, mean and range. When to use. Sample size equals N equals 2 to 10. Small subgroups measured at regular intervals. Examples: measure diameter of 5 rods every hour. Record wait time of 4 customers every shift. Key components: X bar chart, plots mean of each subgroup. R, range chart, plots range, max minus min in each subgroup. Example: manufacturing. Every hour we measure diameter of 5 pistons. X chart, average diameter of 5 pistons. R chart, spread of diameter within the 5 pistons. Detects if process mean drifts and if variability increases. Example: service. A hospital records wait time for 3 patients every 2 hours. X chart, average wait time. R chart, range between longest and shortest wait. Ensures average wait stays on target and variability doesn't increase. Interpretation: any point outside limits? Is R chart in control? If R out, X unreliable. XS chart, mean and standard deviation. When to use: sample size equals n greater than 2, large subgroups. When you prefer standard deviation over range, more precise for large samples. Examples: measure length of 20 parts every shift. Record handling time of 30 calls every day. Key components: X chart, mean of subgroup. S chart, standard deviation of subgroup. Example: manufacturing. Every 4 hours, measure 20 steel rods for length. X chart, average length. S chart, standard deviation of lengths. Detects shift in mean and tighter control of variability in large samples. Example: service. Call center records handling time for 25 calls every day. X chart, average call time per day. S chart, standard deviation of call times per day. Monitors if call handling stays consistent and stable. Interpretation: are points in control? Is S chart showing stable variation? Key differences. Comparison table. IMR charts are used when you have a sample size of 1 and track individual values and ranges. Ideal for single data points like transaction times. XR charts are suitable for small subgroups, 2 to 10 samples, tracking mean and range, commonly used for measurements like diameter or wait time. XS charts are used for larger subgroups and track the mean and standard deviation. These are mathematically more complex and fit scenarios like analyzing call data over time. IMR and XR charts are easier to interpret, while XS requires more statistical knowledge. Why does it matter? All control charts detect process shifts, unexpected variability, out-of-control signals, but choosing right chart matches. Sampling plan and data collection. Wrong chart equals misleading interpretation. Summary message. Control charts for continuous data are like health monitors for your process. They don't just say good or bad. They show trends, shifts, and stability over time.